Hi Bob, I've been reviewing quantum computing papers from March 2025, and there's been so much interesting research. I'd love to get your thoughts on some of the key developments. What stands out to you from the recent publications?
Hello Alice. March 2025 was indeed a productive month for quantum computing research. Several themes stand out to me. Advances in quantum error mitigation, practical applications in industries like finance and transportation, hardware-software co-design approaches, and significant improvements in variational quantum algorithms. The field is clearly maturing beyond purely theoretical work toward more practical implementations.
I noticed several papers on error mitigation and correction. The paper by Aharonov et al. Particularly caught my attention with its discussion of quantum error mitigation versus quantum error correction. Could you elaborate on their findings about the importance of error mitigation for achieving quantum advantage?
That's an excellent observation, Alice. Aharonov's paper on error mitigation makes a crucial distinction between what they call finite quantum advantage and asymptotic quantum advantage. They argue that error mitigation, EM, will likely be the first error reduction method to achieve useful finite quantum advantages before error correction, EC, becomes viable. They introduce the concept of circuit volume boost to quantify EM benefits. While EM can't enable exponential quantum advantages due to its runtime overhead, they make a compelling case that it will remain important even when EC becomes routine, especially when high-quality qubits remain scarce. This perspective is quite significant for near-term quantum computing.
That's fascinating. Speaking of practical applications, I was intrigued by New et al.'s paper on quantum computing in transportation science. How do you see quantum computing impacting this field specifically?
The New et al. Paper is quite comprehensive in exploring quantum computing's potential impact on transportation systems. They focus on three main quantum paradigms: gate-based quantum computing, quantum annealing, and quantum machine learning. Transportation science involves many complex optimization problems, like route planning, traffic flow optimization, and logistics scheduling, that classical computers struggle with as the problem size increases. Quantum annealing, for instance, could potentially solve large-scale vehicle routing problems more efficiently, while gate-based approaches might handle complex traffic simulations. The paper does a good job of mapping specific transportation challenges to the most appropriate quantum computing approach.
There seems to be a lot of work on improving variational quantum algorithms too. I found the paper by Pankkonen et al. On hybrid algorithms for variational quantum circuit optimization particularly interesting. What's your take on their approach with the rotosolve method, and how significant is it?
The Pankkonen paper addresses a fundamental challenge in the NISQ era: how to efficiently optimize variational quantum circuits, VQCs. Their key innovation is enhancing the rotosolve method by combining it with the free quaternion selection FQS algorithm. This hybrid approach is quite clever. They're leveraging the fast initial convergence of rotosolve while benefiting from the superior expressivity of FQS. Their numerical simulations show a compelling trade-off. More expressive ansatzes can reach closer approximations to the true minimum, but require more circuit evaluations to converge. By combining these methods, they achieve better average performance across different circuit sizes and cost functions. This could significantly improve the practical utility of VQCs, which are central to many quantum algorithms in machine learning, optimization, and chemistry.
That makes sense. I'm also curious about the quantum computing hardware developments. The paper by Rallis et al. Discusses hardware-level interfaces for hybrid quantum classical computing systems. How important is this kind of research for the future of quantum computing?
The Rallis paper addresses a critical but often overlooked aspect of quantum computing: how to effectively integrate quantum processing units, QPUs, with classical high-performance computing, HPC systems. This integration is essential because quantum computers excel at specific tasks but can't function as general-purpose machines. The paper rightly points out that this interconnection between classical and quantum systems isn't standardized yet, which creates a significant bottleneck for practical applications. They focus specifically on hardware-level approaches to this integration, which is crucial for minimizing latency and maximizing throughput. As quantum computers scale up, These hybrid architectures will likely become the dominant paradigm, with QPUs serving as specialized coprocessors alongside CPUs and GPUs. The standardization of these interfaces will be vital for the commercial viability of quantum computing.
That's a great point about hybrid architectures. On a related note, Liu et al.'s paper on hardware-software co-design for distributed quantum computing caught my eye. How does their approach to entanglement generation address the challenges of distributed quantum computing?
Liu's paper tackles one of the fundamental challenges in scaling quantum computing: how to effectively distribute quantum computation across multiple chips or nodes. Their key insight is recognizing that remote entanglement generation, a crucial resource for distributed quantum computing, is probabilistic, slower than local operations, and non-deterministic. Their hardware-software co-design approach combines three innovative strategies: buffering successfully generated entanglement, asynchronously attempting entanglement generation, and adaptively scheduling remote gates based on the entanglement generation pattern. This approach is quite pragmatic, acknowledging the physical constraints of current and near-term quantum hardware, while providing a path forward for scaling beyond single-chip limitations. Their results showing improvements in both runtime and output fidelity are particularly promising for the future of modular quantum computing architectures.
I've also noticed several papers focusing on quantum applications in finance. The papers by Chowdhury et al. On hybrid classical quantum neural networks for financial stock prediction and Imami et al. On financial fraud detection seem particularly interesting. How do these approaches compare? And do you think quantum computing will have a significant impact on financial applications in the near term?
These papers represent different approaches to financial applications of quantum computing. Chowdhury's HQNN-FSP paper proposes a hybrid classical quantum convolutional neural network specifically for stock market prediction, using 3D MRI-inspired data handling. They demonstrate that their model achieves higher accuracy with fewer parameters than classical approaches. Imami's paper introduces CVQ Boost, running on Quantum Computing Inc.'s Entropy quantum computing hardware, which shows significant runtime advantages over classical XGBoost for fraud detection while maintaining comparable accuracy. The Elnaz paper takes a broader view, analyzing how both AI and quantum computing pose cybersecurity threats to financial transactions, particularly highlighting the harvest now, decrypt later vulnerability with quantum computing. Collectively, these papers suggest that finance may be an early beneficiary of quantum advantage, particularly for computationally intensive tasks like fraud detection and risk modeling. The hybrid approaches seem most promising in the near term, combining classical preprocessing with quantum acceleration for specific computational bottlenecks.
That's really insightful. Switching topics slightly, I found the paper by Baumick et al. On enhancing variational quantum algorithms fascinating. They discuss balancing training between classical and quantum hardware. Could you explain how their approach might help address the resource limitations of current quantum devices?
Baumick's paper addresses a crucial practical challenge in variational quantum algorithms, VQAs, the high resource cost of training exclusively on quantum hardware. Their innovative approach combines two training schemes that distribute gradient estimation and training across both classical and quantum hardware. They use the hardware-efficient and dynamical Lie algebra-supported ansatz, Helia, and combine the GSIM method, which leverages group structure, with the parameter shift rule PSR. This hybrid approach reduced quantum hardware calls by up to 60% compared to using PSR alone, which is significant given the limited availability and high cost of quantum computing resources. They also demonstrated Helia's capability to mitigate barren plateaus, a major obstacle in training quantum models. This work exemplifies a pragmatic approach to quantum algorithm development. Rather than waiting for fault-tolerant quantum computers, they're designing algorithms that make optimal use of both classical and quantum resources, potentially enabling practical quantum advantage sooner.
The barren plateau mitigation is particularly interesting. I also noticed several papers on quantum error characterization and mitigation. The paper by Bloom-Kohout et al. Provides a comprehensive overview of quantum characterization, verification, and validation, QCVV. How does this relate to the work by Hossein Khani et al. On noise-robust estimation of quantum observables?
Great question about the relationship between these papers. Bloom-Kohout's paper on QCVV provides the theoretical foundation and overview of techniques used to characterize and benchmark quantum devices. They cover tomography, randomized benchmarking, and holistic benchmarks, essentially the toolkit for understanding quantum noise and errors. Hossein Khani's paper on noise-robust estimation, NRE, represents a practical application of these principles. Their work introduces a specific error mitigation technique that systematically reduces estimation bias through a two-step post-processing approach. What's particularly innovative about NRE is that it's noise agnostic. It doesn't require detailed knowledge of the noise model. Instead, it exploits a bias dispersion correlation they discovered, using bootstrapping on existing measurement counts. Their experimental validation on a superconducting quantum processor with up to 20 qubits demonstrates near bias-free estimations with manageable sampling overhead. So while Bloom-Kohout provides the theoretical framework, Hossein Khani offers a practical implementation that can be immediately applied to current noisy quantum hardware.
That's a helpful explanation of how those papers connect. I'm also interested in the intersection of quantum computing and AI. The paper by Ueda and Matsuo on optimizing ansatz design in quantum GANs using large language models seems like an innovative approach. What are your thoughts on using LLMs to improve quantum algorithm design?
The Ueda and Matsuo paper represents an exciting frontier in quantum algorithm design. They're essentially using one cutting-edge technology, LLMs, to improve another, quantum GANs. Their approach leverages LLMs to iteratively refine ansatz structures, improving accuracy while reducing circuit depth and parameter count. This is quite innovative because designing effective quantum circuits is currently something of an art form, requiring specialized expertise. By automating this process with LLMs, they're potentially democratizing quantum algorithm development and enabling more efficient exploration of the design space. What's particularly promising is that their workflow extends beyond GANs to other variational quantum algorithms, providing a general framework for quantum circuit optimization. This intersection of classical AI and quantum computing could significantly accelerate quantum algorithm development, especially as we're still learning the best ways to structure quantum circuits for different problems. It's a great example of how hybrid approaches can leverage the strengths of both classical and quantum computing paradigms.
That's fascinating. One last area I'd like to explore is quantum security. The paper by Berezitsky et al. On row hammer attacks on quantum computers is quite concerning. Could you explain the implications of this vulnerability and how it might affect quantum computing security?
The Berezitsky paper reveals a significant hardware vulnerability in quantum systems that's analogous to the row hammer attack in classical computing. They demonstrate that by exploiting crosstalk effects on IBM's quantum computer, they can effectively flip a qubit state. Crosstalk occurs when operations on one qubit unintentionally affect nearby qubits, and they show that two qubit operations applied near a target qubit can significantly influence it. This has serious implications for quantum computing security. First, it demonstrates that quantum computers aren't immune to hardware-level attacks. Second, it suggests that adversaries might be able to manipulate quantum computations without requiring direct access to the target qubits. This could potentially compromise the integrity of quantum algorithms, especially in cloud-based quantum computing environments, where multiple users share the same hardware. As quantum computers become more widely used, especially for security-critical applications like cryptography, addressing these hardware vulnerabilities will be crucial. It also highlights the importance of developing quantum-specific security protocols and hardware designs that minimize crosstalk effects.
That's definitely concerning for quantum security. Looking at all these papers together, what do you think are the most promising directions for quantum computing research in the coming year?
Based on March 2025's papers, I see several promising directions. First, hardware-software co-design approaches like Liu's distributed quantum computing work will be crucial for scaling beyond current hardware limitations. Second, Hybrid classical quantum methods, as seen in Baumik's and Chowdhury's papers, will likely deliver the first practical quantum advantages by optimally using both resources. Third, error mitigation techniques, as Aronov and Hosenkani emphasize, will remain essential for near-term quantum utility. Fourth, the integration of AI with quantum computing, demonstrated by Ueda's LLM approach, could accelerate algorithm development. Finally, I expect increased focus on industry-specific applications like those in finance and transportation, where quantum computing can address well-defined computational bottlenecks. The field is clearly transitioning from proving quantum advantage in contrived scenarios toward solving practical problems, with an emphasis on making the most of limited quantum resources through clever algorithmic and architectural innovations.
Thanks so much for this insightful discussion, Bob. You've really helped me understand the connections between these papers and their significance for the field. It's exciting to see quantum computing research moving increasingly toward practical applications, while still addressing fundamental challenges like error mitigation and hardware limitations. I'm particularly intrigued by the hybrid approaches that leverage both classical and quantum resources. They seem like the most promising path to near-term quantum advantage. Thanks again for sharing your expertise.